This is the Chapter 6 review questions from Berean Builders Discovering Design with Physics. So as usual, I am not going to go over these definition terms because you can easily find those in the book. And so we'll skip on ahead to question 2. For each situation, indicate whether or not the object is in translational equilibrium. If it is, indicate whether the equilibrium is dynamic or static. So for A, an object moving in a circle with a constant speed, this would not be in translational equilibrium. And the reason for that is because it's in a circle, the velocity is constantly changing because the velocity is constantly changing in direction. And so if that velocity is always changing, it's not equilibrium. For B, an object moving due east with a constant speed, yes, that object is in translational equilibrium and it's going to be dynamic, right? So the velocity is not changing, the acceleration is 0, and so there's no force being applied there. And because it is moving, it is dynamic, translational equilibrium. And then for C, an object at rest, of course, that is also in translational equilibrium. There is no force being applied there, and it's not moving at all, and so it would be static translational equilibrium. For question 3, in most automobiles, the seatbelt is loose so that it can move with the person as he or she adjusts position. However, when the brakes are hit hard or a collision occurs, the seatbelt locks so that it holds the person in place. What must the seatbelt system have in order for this to work? And so if you think back, part of the book was talking about accelerometers. That is what is actually going on with the seatbelt. The seatbelt must have an accelerometer. And so when the brakes are hit or a collision occurs, the velocity changes, which means that there's an acceleration, and an accelerometer detects that, and the seatbelt is then locked. For question 4, a sign is hung as shown in the diagram on the right. If the sign has a mass of 5.60 kilograms and the strings are of equal length, what is the tension on each string? So let's go ahead and write out what we know. Okay, we have this angle that is 41.4 degrees. We know the mass is 5.60 kilograms. And that is all that is given to us to start. But there are other things that we can definitely figure out. And we know for this type of problem, we're going to need the angles that are connecting the string to the sign. Okay. And specifically, we need the physics angles. So we need this one right here, as well as this one. Okay. And so remember, our physics angles are always coming from this point here and going this way, right? And so that's why we need that. So to determine this, we can use this angle that we're given, 41.4. And because these strings are of equal length, we know that these two angles are going to be equal. And we know that all of the angles in a triangle add up to 180. And so for our angle of T1, we're going to call this T1 and this T2, okay? That is going to be 69.3. And so how I got that is 180 minus 41.4 and divide that answer by 2 and you get 69.3. So this is 69.3 and this is 69.3 right here. Now we don't want this 69.3 for the T2. We need the other side of it. And so again, we're just going to use some geometry there and determine the opposite angle here is going to be 180 minus 69.3. And so our angle for T2 is going to be 110.7 degrees. And so now we know enough that we can solve this problem. Okay, so we're going to use our x dimension and y dimension equations to then solve for T1 and then determine T2. Okay, so here's our x dimension equation. We have T1 times the cosine of 69.3 plus T2 times the cosine of 110.7. Okay, and then technically here, the next thing would be having plus the weight times the cosine of 270 because the weight is pulling this down. The angle is 270. But the cosine of 270 is 0. So we're not going to even write that part, but that is technically included as part of this equation. Okay, and so then I'm just going to make those equal to 0. Okay, and then my y dimension this problem, you have kind of almost the same, basically the same thing, except we're using sine. So we have sine of 69.3 plus T2 times the sine of 110.7 plus, and here we are going to go ahead and write that last part, the weight times the sine of 270. Okay, and all of that is equal to 0. Okay, so sine of 270 is always going to equal -1, just so we know that. Okay, so now we're going to solve for T1, and so we're going to take this simpler equation and solve for T1. And so when we do that, T1 is going to equal negative T2 times the cosine of 110.7 divided by the cosine of 69.3. So that's just taking this equation and you subtract T2 and T2 and cosine of 110.7 and then divide by cosine of 69.3. So this is solving for T1, and so now we can let's simplify this a little bit. So equals negative T2 times -1. Okay, and so if you have negative T2 times this cosine 110.7 divided by cosine of 69.3 is -1. And so that's simply T2. So T1 equals T2. So now we're going to plug it in. So we're going to plug in this T1 equals T2 into the y dimension equation and solve for T2. So instead of writing T1 here, I'm going to write T2 times the sine of 69.3 plus T2, I'm just rewriting this, times the sine of 110.7 plus, let's go ahead and plug in the weight values. So we have 5.60 kilograms times 9.81 meters per second squared times -1. So notice I didn't do a negative 9.81 in this particular case. The numbers are just magnitude, so we're not assigning direction and therefore signs to the value of gravity. Okay, so mass times gravity equals weight, and then that times 1 is sine of times -1, I mean, is sine of 270 is -1. Okay, so I have my weight, 5.6 kilograms, 9.8 times 9.81 meters per second squared, and sine of 270 is -1. And all of that set is set to equal to 0. Okay, and so when I do sine of 69.3, I get 0.935 times T2 plus sine of 110.7 is also 0.935 times T2 plus, sorry, it's going to be minus because we have that -1. So say minus 54.9 newtons. We have kilograms times meters per second squares, and that is simplified as newtons for my unit, all equal to 0. Okay, so now I'm going to simplify these further and move this over, and so I get 1.87 times T2 equals 54.9 newtons, and then divide by 1.87, and T2 equals 29.4 newtons. Okay, and therefore T1 also equals 29.4 newtons because T1 equals T2. Okay, so now we've determined both tensions, and we have our answer. The tension on each string is 29.4 newtons. For question 5, another sign is hung as shown in the diagram on the right. If the tension in the string on the right is 11.6 newtons, what is the mass of the sign and the tension in the string on the left? Okay, so we know here that our T2 equals 11.6 newtons. That is our tension 2. We need to figure out this T1 as well as the mass of the sign. So what we're going to need to figure out first is our angles that are from where the string connects to the sign. Okay, and so for T1, how we're going to do that is we're going to use the fact that when two parallel lines are cut by a transversal, the alternating interior angles are congruent. Okay, so this is the interior angle, 47, and then this is an interior angle. And so both of these angles have to be 47. However, we're not looking for this angle. Our physics angle needs to be the one on the right. Okay, and so for that, we're then going to use the rule that, when you have a straight line and it's cut by a transversal, the opposite sides of this angle of this line add up to 180 degrees. Okay, and so we're going to take 180 minus 47, and so our angle of T1 is going to be 133 degrees. Okay, for our T2 angle, this is the angle that we want, and again we're going to use that rule about a transversal cutting through parallel lines, and these are both the interior angle, and so our angle for T2 is going to equal 28 degrees. Okay, so now that we have the angles and we have T2, we can use the X dimension to solve for T1. And so let's plug in that equation. We have T1 times the cosine of 133 degrees plus T2, and actually we're going to write that number in because we have it. So T2, which is 11.6 newtons, times the cosine of 28, taking that angle. You know, and again, once again, technically we have the plus the weight of the cosine of 270, but that equals 0, and so we're not going to even write that. And so all of this is set to equal 0. And so when we take this 11.6 times the cosine of 28, put it on this side, and divide it by the cosine of 133, we're going to get T1 equals 15 newtons. Okay. So we're not done yet because we've determined the tension, but we still need to determine the mass of the sign. So to do that, we're going to use the y dimension equation. And so for the y dimension equation, we have T1 times the sine of T1 plus T2 times the sine of T2 minus the weight. And so and that is all equal to 0. So let's plug those numbers in. T1 is 15 newtons. Oops. Times the sine of 133 plus T2, 11.6 newtons, times the sine of 28. Okay, and instead of saying minus weight equals 0, I am going to just go ahead and move weight to the other side. Okay, so let's just add this up. You have 15 newtons times sine of 133, and so we get, with appropriate two significant figures, we get 11 newtons plus 11.6 newtons times the sine of 28 is going to be and equals the weight. Now when we add these together, we can, by significant digits, it's just going to be to the ones place because we're adding. And so it's just 11 plus 5, and 16 newtons equals the weight. So now weight equals mass times gravity, right? And so now I'm going to divide this by 9.81 meters per second squared. And so that's going to give me the mass. And I will get 1.6 kilograms as the mass of the sun. So the tension in the left string is 15 newtons, and the mass of the sign is 1.6 kilograms. For question 6, the coefficients of friction between a 15 kilogram box and a ramp are 0.42 and 0.29. At what angle will a box at rest just start sliding down the ramp? And then our second question, so we have two here, is at what angle will a box slide down the ramp with a constant velocity of 4.1 meters per second? There are two parts of this question that are not relevant. Okay, the 15 kilogram box, mass does not matter to this equation. It does not change how something slides down a ramp. And the constant velocity of 4.1, the number here doesn't matter. The constant velocity is the key because that's telling us that we are in dynamic translational equilibrium. And so we're looking for that number. So for the static translational equilibrium, we need to find the angle that satisfies our equation 6.6, which was mu equals tangent of the angle. And so we're just going to fill in these numbers. So our static friction is the larger of the two numbers, so 0.42. And so it's 0.42 equals tangent of our angle. Or you can say inverse tangent of 0.42 is going to equal our angle. And so we do that and we get 23 degrees. And so 23 degrees is the angle at which we are maintaining static translational equilibrium. And any angle that is greater than this, that box is going to move, okay, on its own. Now the second question is asking at what angle will a box slide down the ramp with a constant velocity? And so it's been given some kind of push to start with, and we want to know what the angle is that after it's been given that initial push, it will just keep going down the ramp at a constant velocity. And so for that one, we're going to use the same equation, but we're going to plug in the lower friction component, which is our kinetic friction for mu. Okay, and so I'm just going to use this here that's already been modified to a way that we're plugging it into our calculator. So inverse tangent of 0.29 is going to equal our angle, and that is going to give us 16 degrees. Okay, so our answer then is the box will start to slide at any angle greater than 23 degrees. It will slide at a constant velocity at an angle of exactly 16 degrees. Okay, so that if this angle is lower, it will have a drop in velocity. Okay, so it'll have a negative acceleration. If this angle is higher, it will be accelerating. It will have a positive acceleration. And so for dynamic translational equilibrium, this angle has to be exact if you're trying to maintain that equilibrium. And so that's why in the second part, the angle needs to be exactly 16 degrees, whereas in the first part, we're just getting it started moving, and so it has to be greater than our angle for static translational equilibrium. For question 7, a box is placed on an incline in which the angle is 25.4 degrees. Will it begin to slide down the ramp? Then the second part is if it is given a shove, will it achieve either form of translational equilibrium? Third part, if not, what is its acceleration? And it tells us what the coefficients of friction are. So that 0.59 is going to be static, and the 0.37 will be our kinetic. Okay, So we can use the same formula. Here's the last problem. Mu equals tangent of theta. Okay, and there are two ways that we can use this formula for the first part of the problem. So I'm going to demonstrate both ways because I actually used a different way than the solutions manual showed. And so it's like, okay, great. There's two ways I can show you how to do this. So the way I first used was to take the theta that we're given, the 25.4 degrees. Okay, so equals tangent of 25.4, and I get for my mu, then I got 0.47. Okay, now what does this mean? It means that this box at this angle would slide on its own at any static friction coefficient that is below this number. Okay, and so our static coefficient of friction is 0.59. It's not below 0.47, so it will not slide on its own down the ramp. Okay, then the second part is if it's given a shove. Okay, so if we're talking about dynamic translational equilibrium, this number means that if the coefficient of friction, the kinetic coefficient of friction, is exactly this number, then yes, it would have dynamic translational equilibrium. But it does not, right? 0.47, 0.37. And so the first answer here is no, it's not going to slide down the ramp. The second answer is no, it will not achieve either form of translational equilibrium. Okay, now the second way that you can solve this is solving for mu, using the mu's that were given, the coefficients of friction that were given. And so we can plug in, have inverse tangent times our mu. So let's do 0.59. And we get 31 degrees here. Okay, and what that would mean is that this box would only start to slide on its own if the angle was greater than 31 degrees. It is not, it is 25.4 degrees, and so therefore it will not slide on its own. Okay. Now, then the next thing that we can do, and you could do the same thing for the dynamic translational equilibrium with the kinetic coefficient of friction, and determine that yes, it would be sliding on its own at that point, but it would not be that exact angle, and so it would be sliding faster. So now we need to determine what its acceleration is going to be. And so we're going to be adding the forces to get the net force. Okay, so we have our normal force plus our friction, and that's going to equal our net force. Okay, common equation that we've used over and over again in this course already. Okay, so when we're doing the normal force, we have a negative in front of it because this is the force that normal force is going down, pushing down, and our friction is pushing up. Okay, and so we're giving a negative sign to these just to denote direction. Okay, and so our normal force is going to be our mass times gravity times our sine of theta. Okay, then we'll be adding our force due to friction, and so we have our kinetic coefficient. We have mass, gravity, and it'll be times the cosine of theta here. And so actually I have this arrow up and down, but really what we are doing here is the normal force is going down at this angle. Okay, and our friction is pushing up at this angle. Okay, so ignore what I just did there. Okay, and so that's why we are using sine and cosine, because we are using the angle there. Okay, and so then that is going to equal our net force, which is going to be our mass times acceleration. Okay, now notice in all three parts of this, we have mass. Okay, and lucky for us, because we weren't given mass, we can now cancel out all of those masses. Okay, so mass is not relevant to this type of problem. It ends up just canceling out. So let's go ahead and fill all this in. Negative 9.81 meters per second squared times the sine of 25.4 plus our kinetic coefficient, 0.37, times 9.81 meters per second squared times the cosine of 25.4 equals our acceleration, which is what we're trying to find out. Okay, so this part here is going to be negative 4.21 meters per second squared, plus this part here is going to give us 3.3 meters per second squared. Okay, notice three significant figures. Here we just have two because of this 0.37 from our kinetic coefficient of friction. And so that's going to all equal our acceleration. We have to have our answer to the 10th place because we are adding and this only goes to the 10th place. And so we're going to have negative 0.9 meters per second squared equals acceleration. Okay. So long answer here, right? Because we've got three parts. Part one, will it slide down the ramp? The box will not slide on its own. Upon pushing, so it's given a shove, it will be in neither of the translational equilibriums. It has an acceleration. Okay, and its acceleration will be negative 0.9. And actually, we're going to write this down just more conversationally. Its acceleration. So this negative means it just means it's going down. All right. That's what we use to denote direction. All right. So its acceleration will be 0.9 meters per second squared down the ramp. Okay. And so that is our answer for that. We've answered all three parts of that question. For question 8, a box accelerates down a ramp at 2.6 meters per second squared. If our angle is 31.3 degrees, what is the coefficient of kinetic friction? So we know that we're not in translational equilibrium because we have an acceleration. And so what we're going to need to do is sum up our forces. So again, we have our normal force plus our force due to friction, and that equals our net force. Okay. And so just like before, we're going to write those out. So remember that normally force has mass as a component of it, but it's going to cancel out in all these cases. And so we're going to ignore mass, which is great because we weren't given mass. And that would be impossible to figure out. So we're going to have, actually, I'm going to highlight this. We have an acceleration, and just to give it a direction for this equation, we are going to say that it's down equals negative. Okay. Okay, so our normal force is going to be, it's going to be negative gravity times the sine of theta. Okay, then we'll be adding our force that's due to friction, and so we'll have mu k, which is our unknown, times gravity times the cosine of theta, and that's going to equal our mass times acceleration, but we're not having mass, so equals acceleration. Okay, so now let's plug in what we know. Negative 9.81 meters per second squared times the sine of 31.3 that we were given, plus kinetic coefficient of friction is unknown, times 9.81 meters per second squared times the cosine of 31.3. And that's going to equal our gravity, or sorry, not gravity, our acceleration. That is 2.6 meters per second squared. Okay. And so now let's go ahead and simplify this. So 9.81 times the sine of 31.3, we get negative 5.10 meters per second squared, plus our mu k times these multiplied together are going to get us 8.38 meters per second squared equals, oops, this was supposed to be negative, okay, negative 2.6 because we were going down that ramp, meters per second squared. Okay, and so now we will add 5.10. Okay, we got to keep it to the 10th place because this 2.6 only goes to the 10th place. And so then on the right side, we get 2.5 meters per second squared when we add negative 2.6 plus 5.1. And okay, and so then we're going to divide, and we're going to, our answer is going to be to two significant figures. And so when we divide 2.5 divided by 8.38 meters per second squared, we get 0.30, which has no units because these canceled out, which is exactly what should have happened because our coefficients of friction do not have units. And so that's our answer. The coefficient of kinetic friction is 0.30. For question 9, a toy truck with a mass of 55.0 grams is pulled east with a force of 1.75 newtons. It is attached by a string to a toy car with a mass of 42.3 grams. what is the acceleration of the cars and the tension in the string, and ignore friction. Okay, so we are back to some vector quantities here. We are being told that this is being pulled east with a force of 1.75 newtons. Okay, and so we are going to say that east here is positive. And remember that we're going to have acceleration in our answer, and we're going to need to include that direction with it. Okay. So I haven't been writing down all my givens on some of these, but this one I'm definitely going to, because there's, several different parts, right? So we have our mass of our truck, which I'm going to designate with M of T, and it's 55 grams, but we're using newtons, and so I'm going to go ahead and convert that to kilograms, keeping my significant figures in there. Okay. So the force of this truck, and it's also our total force. And so I'm going to call it actually the total, because this truck is pulling everything. Okay. And it's going to be 1.75 newtons. Okay. Our toy car, so we have mass of C, our car, is 42.3 grams. And we're going to convert that also to 0.0423 kilograms. And then we need to know the acceleration of the cars and the tension in the string. Okay, so for me, the acceleration problem is really, really simple, because force, our total force, equals mass times area. Okay, and so therefore, or not area, acceleration. Okay, and so therefore acceleration just equals force divided by the mass. Okay, so our total force here is 1.75 newtons. And when we do the mass, though, this force is pulling both of these cars. Okay, both the truck and the car. And so the mass is going to be the total mass. So the car plus the mass of the truck. Okay, and so that equals 1.75 newtons divided by, I don't have the exact number here, so divided by 0.0973 kilograms. There we go. And that gives us 18.0 meters per second squared, and it's positive, and so I'm just going to go ahead and write this in east. Okay, so that is the total acceleration, the first part of these cars. So the second part, we need to determine what the tension is right here. So now we need to determine what the tension is in the string. Okay, so I'm just going to use this. We're not going to totally use this equation here, but force, the total force is the addition of the force of the car plus the force of that truck, right? So that total force was 1.75 newtons. We could figure out the force of the truck by taking the mass times the acceleration of the truck. But now we can also figure out what the force of the car, which is the same as the tension, right? Equals the tension. This is the force that's acting on the car, is this rope pulling it. We know the acceleration. So we're just going to say mass times acceleration. Force is mass times acceleration. So we have the mass of the car. We have the acceleration that both of these little vehicles are doing. And so we can determine the force that's acting on the car, or the tension, otherwise known as tension. So equals So mass times acceleration is what we're doing, not the total force, equals 0.0423 kilograms times 18.0 meters per second squared, and that is going to give us 0.761 newtons. Okay, so our final answer for the first part, the acceleration, is 18.0 meters per second squared east, and the tension in the string, which is the force that's acting on the car, but it's asking us about tension, is 0.761 newtons. And that's my answer. For question 10, the force in problem 9 is changed so that the same system produces a tension of 0.93 newtons in the string. What is the magnitude of this new force? And we're going to continue to ignore friction. So now we have the tension of the car, which is, tension of the string that's controlling the car, 0.93 newtons. Okay. And so force equals mass times acceleration. Okay. So let's determine some new numbers from this. Okay. So we have the total force. We have the mass from our previous problem, which on the car was 0.0423. Okay. So our force, 0.93 newtons, equals our mass, 0.0423 kilograms times acceleration. So let's use this first to determine the acceleration. And so 0.93 divided by 0.0423, we have two significant figures here, so it's going to be 22 meters per second squared equals the acceleration. Okay. But that's not quite what we're asking for. We need the magnitude of this new force. All right. So we're trying to get that F total again. Okay. And so our F total is going to equal the tension in the car plus that force of the truck, right? Now we were given the tension of the car, but why we needed acceleration is so that we can determine the force of the truck. Okay. And so the tension in the car is what we were given, 0.93 newtons. For the force of the truck, we're going to use mass times acceleration, and now we have acceleration. And so our mass from before on the truck is 0.0550 kilograms. And we're multiplying that times 22 meters per second squared. And so that's going to give us 0.93 newtons plus 1.2 newtons. We have to stay two significant figures because of this 22 meters per second squared. And then we're going to have to just keep it to the 10th place here, because of significant figures rules with adding. And so we're just going to get 2.1 newtons. And so that's our total force. So the new force is 2.1 newtons. For question 11, a strong man tries to unscrew a pipe with a wrench. He uses all his strength, but the pipe will not unscrew. A young girl uses a different wrench and unscrews the pipe easily. Compare the lengths of the two wrenches. Okay, so this is about torque, and the larger the radius is, the more rotational force that you have. So the wrench that the young girl is using is much longer than the one that the strong man used, therefore giving her more rotational force, more torque on the wrench to unscrew that pipe, and that's how she's able to do it. For question 12, for each of the following situations, indicate which diagram, either 1 or 2, shows the larger net torque. So for A, the number 1 diagram is showing larger torque because this lever arm is longer. For B, 2 is giving us the larger torque, and that's because this force that is pulling down is perpendicular, and so it's all counting towards the torque versus this one, which is not. And then for C, 2, diagram 2 is also going to be giving the larger net torque, and that's because both of these are pulling pulling clockwise, and so therefore those forces are additive and increasing like a higher force, whereas these are pulling in opposite directions, and these forces are going to cancel out, and so 2 has the larger net torque for C. Question 13, 2 objects are placed on a balance so that it doesn't tilt. The first, which with a mass of 214 grams, is put 12.1 centimeters left of the axis of rotation, while the second is put 7.1 centimeters right of the axis of rotation. What is the mass of the second object? Okay, so I'm going to go ahead and write out what we're given. We have a mass of the first object is 214 grams. The radius, the distance away from the axis of rotation, is 12.1 centimeters. Okay, we're going to say, we'll leave it at that. Okay, and then the second one, the mass is unknown, but our radius equals 7.1 centimeters. Okay, and so our equation, a rough equation that we are using, is our first torque. It's going to be minus the second one, and the reason it's minus is this one is, you have this axis of rotation here. Okay, this one is pushing down here, and this one's pushing down here, and this pushing down is causing a counterclockwise motion, which is pushing this side up, and so that gives this one actually a negative force. Okay, and so that's kind of how they cancel out. All right, and they have to cancel out and equal 0 because they are perfectly balanced and not tilting. Okay, so our first torque minus our second torque, and I'm not drawing the torque symbol very well. There you go, torque, equals 0. Okay, and so our torques are going to be simply our it's going to be our mass times, technically it's mass times gravity times the radius, because it's the perpendicular force, right, times the radius, so mass times gravity, but the gravities are going to cancel out, right, because we're going to have times gravity, and it's subtracting, and so we don't actually need to put gravity into these equations for this problem. Okay, so our mass of our torque 1 is 214 grams times our radius, 12.1 centimeters, minus our unknown mass, mass 2, times our radius of 7.1 centimeters. Okay, and all of that equals 0. Okay, so 214 grams times 12.1 centimeters, we get 25.90 grams times centimeters. Notice on this one, we don't have to change any of the values because we don't have newtons in here. And so we don't have to change any of the units to fit some other units in the problem. Okay, so 2,590 grams times centimeters. We have three significant figures here, so that's why it's 2,590 equals our mass of 2 times 7.1 centimeters. So we'll divide both sides by 7.1 centimeters. And so our mass ends up being 360 grams. Two significant figures here, okay? So technically it was 364.8 when you did this division, but 360 is our answer with significant figures. Okay, so the mass of the second object is 360 grams. And just double checking that that is all it's asking us. So what's the mass of that second object? And we're good. Question 14, we have three objects that are placed on this balance as illustrated, and we want to know what the mass of the blue object is. So for our additive torque equation here, we have our T1, which is our blue. I'm calling this T1. We'll call this T2. And then this T3. So T1 minus T2 minus T3 is going to equal 0. Okay? And so we can just plug in everything that we know about each of these torques and solve for the mass of T1, okay? So once again, gravity would be included because technically gravity is part of the force, but it's going to cancel out, so we're not going to worry about gravity. So T1, we have mass times our radius, 19.6 centimeters, okay, minus T2, our mass is 56 grams, times 4.3 centimeters, minus T3, our mass is 45 grams, times, this is not 11.2 centimeters. We need to make sure that we are taking it all the way to the axis of rotation, okay? So it's going to be 11.2 centimeters plus 4.3 centimeters, which equals 5.5 centimeters. Or sorry, 15.5 centimeters. And all of that equals 0. Okay, so I'm going to add these and move them over to the other side. Well, we'll go ahead and add them first. Okay, so we have our mass times 19.6 centimeters minus, let's determine 56 grams times 4.3 centimeters is 240 grams times centimeters. Okay, two significant figures here. Minus 700 grams times centimeters. Now, technically, there's two significant figures. It was actually like 690 something. 697.5 is, you know, the full answer. And then, but we need it to be two significant figures because of this 45 grams. So technically it would be 7.0 times 10 to the second. But since I'm just in the middle of working the problem, I'm not going to write it that way. And instead I'm going to underline here these two figures. And that's telling me, hey, this is two significant figures that are included in this part of the answer. Okay. Or this part of the working the problem. Okay. So now I can add these together and move them over to the other side. And so I'm going to get a positive 940 grams times centimeters on this side, and still have the mass times 19.6 centimeters. Divide both sides by 19.6. Okay, and so our mass ends up being, we have to stay with two significant figures because that's what this one was here. And so our mass is equal to 48 grams. Okay, so the blue object is 48 grams. All right, and that is it for these Chapter 6 review questions. If you have any questions, feel free to leave them in the comments.